You guys had your last solids and fluids lecture today, so I'm going to start on thermo, and I realize that you guys haven't had any thermo lectures yet, but again, it's stuff that you're going to go over, so don't be too worried if you don't understand what I'm talking about. Okay. Right. Okay, so our first one here is about heat conduction, so the transfer of heat. So as you all know, I'll just go over the basic concepts around thermo. So thermodynamics, the whole module is just about heat energy, so temperature. Obviously things are cold and things are hot, and so when you touch ice, you'll say it's cold, but there's really no such thing as being cold. It's more like the absence of heat. So that ice is cold because it doesn't have as much heat energy as you do, and so the ice cube isn't transferring its cold onto you. What it's doing, what's happening is that you're losing your heat, and your heat is being transferred to the ice cube. So that's why your hand becomes colder, is because your hand has just lost heat energy, right? So it's now less hot, and that's cold. So we can calculate the amount of heat. So heat is a type of energy, and we can calculate the amount of heat that has to be transferred in order to change the temperature. And depending on what kind of material it is, you need more energy to change the temperature by the same amount. So we call that the heat capacity. So the heat capacity is the amount of energy or heat that's required to raise the temperature of 1 kg of that material by 1 Kelvin, or 1 degree Celsius. So that's the heat capacity. And depending on what material that is, it's going to be different. So some materials, like metals, you can increase the temperature quite quickly, whereas some other materials, you have to, they'll absorb a lot of heat before they actually increase the temperature. So you'll notice that I used the unit Kelvin. So Kelvin is a unit of temperature, and in physics, that's the scientific unit, not Celsius. 0 degrees Celsius is equal to 273.15 Kelvin. Okay, so if you want to turn anything, if you want to turn degrees Celsius into Kelvin, then you're just going to add 273.15, okay? And it's important that you convert Celsius into Kelvin, but there's certain situations where you don't have to do that, okay? So I'll tell you when that is, but when you're using temperature in physics, you have to use Kelvin, okay? It's just a different unit. Oh, and my voice is a bit weird at the moment because I was a bit sick last week. So hopefully you guys can hear me okay. So our first question, how much heat must be transferred to a 100-gram block of copper in order to raise its temperature from 20 degrees Celsius to 1084 degrees Celsius? And we want that in kilojoules. And they've told us the heat capacity of copper which is 377 joules per Kelvin per kilogram. Okay, so the equation that we're going to use is Q is equal to mass times the heat capacity, which is C, multiplied by the change in temperature. Okay, so Q is heat energy, so Q is for heat. Okay, so the unit for heat energy will also be joules because it's just a type of energy. Okay, so we'll write down the variables that we have. We know that the mass is 0.1 kilograms because that's 100 grams. And we know that the heat capacity is going to be 377. And so we want to figure out what delta T is going to be. So the change in temperature. Change in temperature is just final temperature minus the initial temperature, which is going to be 1084 is our final temperature, minus our initial temperature of 20. So our change in temperature is 1064. So the thing here, remember that we have to change Celsius into Kelvin, but if you have a change in temperature, if you're using delta T, then you don't have to convert your units beforehand, because what we've done here is we've found the change in temperature in Celsius, but that will be equal to the change in temperature in Kelvin, right? Because imagine if you just added, so if you added the initial temperature in Kelvin would have been 293 Kelvin, and the final temperature would have been 1357 Kelvin. And so if you did delta T equals 1357 minus 293, that should also be 1064. Okay? So when you're using delta T, you can just use the Celsius value, because that's going to be equal to the Kelvin value. Okay? All right, so we have all our values that we need. So now the amount of heat that's needed is going to be 0.1 times 377 times 1064, which will give us 40,112.8 joules. And we want to turn that into kilojoules, so we'll divide that by 1,000, and that'll give you 40.1 kilojoules. Okay? Sweet. And then our next one, we have a flat metal plate, which has a cross-sectional area of 2.5 meters squared at a temperature of 20 degrees Celsius. There's a circular hole in the center of the plate with a radius of 5 centimeters. When the plate is heated uniformly, so when the plate is heated uniformly to 120 degrees Celsius, the radius of the hole increases to 5.01 centimeters. What is the linear coefficient of thermal expansion of this metal? So 5 centimeters. And so when you heat this plate, so what happens to things when you heat them up is that they're going to expand. So depending on what material it is, it's going to expand at different rates. So you can give materials a coefficient that describes how much they're going to expand. So that's the linear coefficient of thermal expansion, and linear means in one direction. Okay, so yeah, sure. And so when this whole plate is going to expand, and because there's a hole in the middle of the plate, when the plate expands, what people think, you might think that the hole might get smaller, but what happens is that everything moves outwards, okay? So the hole is also going to get bigger, right? So then the radius of this hole is going to increase, okay? So the radius of the hole is now going to become 5.01 centimeters, okay? So that's a bit of an exaggeration there, like regarding the increase of the size, but just so you can see. And the equation that you'll use is the change in length is equal to the original length multiplied by the coefficient multiplied by the change in temperature. Okay? So delta L is change in length, LO is original length, that's the coefficient, and that there's the change in temperature. Okay, so again, now we want to find the coefficient. Okay, so we're going to have to rearrange this equation for the coefficient. So divide both sides by LO and T. So that'll be delta L is equal, coefficient is equal to delta L over LO multiplied by delta T. Okay, and so now we need to figure out the change in length. So we went from our final, it's always final length minus initial length. So our final length is going to be 5.01 centimeters. 5.01 minus our initial length of 5 centimeters. So that's going to be 0.01 centimeters. And we need to convert that into meters. So that's going to be 0.01 times 10 to the negative 2 meters. Or you could just rewrite that as 1 times 10 to the negative 4 meters, because there's going to be 2 more zeros, right? Okay. So that's our change in length. All right, so now we'll just put in the numbers. Our change in length is 1 times 10 to the negative 4 over our original length, which is 5 centimeters. So 5 times 10 to the negative 2 meters multiplied by our change in temperature. So it went from 20 to 120, so that's just 100 degrees. And that's going to give you 2 times 10 to the negative 5. And the unit is per Kelvin. Okay, so for each degree of Kelvin, that's how much the plate will expand. Okay, and then, so you can see there that you didn't need to know the area of that plate. That was irrelevant. In an X-ray machine, a beam of X-rays pass through a circular hole in a lead plate. When the X-ray machine is switched on, this plate is heated uniformly from 12 degrees to an operating temperature of 255 degrees. At 12 degrees, the hole in the plate has a diameter of exactly 3.000 millimeters. What's the diameter of the hole at the operating temperature? Okay, so this is pretty similar to our last one. if we just imagine that this is the hole in the plate, it's going to absorb heat and it's going to get heated up. So it's the diameter the diameter of this hole will increase, right? Okay, so we need to find out how much it's going to... We want to know the final diameter, so what we need to do is we need to find out the change in diameter, or the change in length, right? Okay, so we'll just figure out the variables that we need. So we're going to use the same equation as the last time. So that's going to be delta L is equal to LO times the coefficient times change in temperature. And we'll just leave it like that now because we just want to know the change in length. So our change in temperature, so first of all, our LO is going to be 3 millimeters, so 3 times 10 to the negative 3 meters. It's a good idea to convert your units before you put them in. And then we know the coefficient, and then we need to figure out the change in temperature, so that's just 255, our final temperature minus our initial temperature, which gives us 243. And remember, you don't have to convert that because we're dealing with delta T. Okay. So then 3 times 10 to the negative 3 times our coefficient, 2.9 times 10 to the negative 5 times our change in temperature, which is 243. So that's going to be 2.1141 times 10 to the negative 5 meters. Okay, so that's our change in length. That's not our final answer because we need to add that to our initial length in order to find out what our final length is going to be. So that's going to be the final length is equal to the initial length plus the change in length. So that will be, the initial length was 3 times 10 to the negative 3 plus 2.1141 times 10 to the negative 5. And that should give you 3.02 times 10 to the negative 3 meters, which is 3.02 millimeters. Okay? Okay, so next we have a thermometer containing 0.015 milliliters of mercury at a temperature of 0 degrees Celsius. The temperature increases to 60 degrees Celsius and the volume of the mercury increases to 0.01516 milliliters. What is the volumetric thermal expansion coefficient of mercury? Okay, so I'll just write this down. So this should be on your cheat sheet as well. So this is your delta L. So for thermal expansion, you've got your linear coefficient, your linear expansion, which is delta L. And then you can also have expansion of area. So if you're looking at 2 dimensions, so the change in the area is going to be the initial area multiplied by 2 times the linear coefficient multiplied by the change in temperature. Okay? So when you're trying to find the change in area, you just multiply the linear coefficient by 2. And then when you want to find the change in volume, you're going to use the original volume, multiply that by 3 times the linear coefficient times the temperature. Because remember, if you have a cube, right, so in one dimension that's linear, and then if you want the area, that's 2 dimensions, so that's just 2 linear coefficients, and then if you were after volume, it's going to expand in 3 dimensions, so that's why you have 3 the multiples of the coefficients. Okay, so what we want to do here, we want to find out the volumetric thermal coefficient. So this is our volumetric thermal coefficient, okay? And that's what we're looking for. So we'll have to rearrange this equation, right? So delta V is equal to VO times 3 times delta T. Okay, so we just want this on its own. So 3 times the coefficient is going to be delta V over VO times delta T. Okay, so that's our equation. So now here, we need to know the change in volume. So remember that in physics, we're using meters cubed, not liters. Okay, so 1 meter cubed is equal to 1,000 liters. Okay, so that means that 1 liter is equal to times 10 to the negative 3 meters cubed. 1 times 10 to the negative 3 meters cubed. Okay, so and 1 milliliter is 1,000th of a liter, so that means that 1 milliliter will be equal to 1 times 10 to the negative 6 meters cubed. Okay, so you need to make sure that you get those right units. So here we're talking about milliliters, so that's going to be our change in volume is going to be our final volume, which is 0.01516 times 10 to the negative 6 minus our initial volume, which is 0.015 times 10 to the negative 6, because that's in meters cubed. And that's going to be over our original volume, which is 0.015 times 10 to the negative 6, and multiplied by our change in temperature. So our change in temperature is just 60. Okay, so that's going to be 1.7777 times 10 to the negative 4, or you can round it to 1.8 times 10 to the negative 4. Okay, so our next one is number 5, a 100-gram piece of bone with a specific heat of 3,500 is placed in a well-insulated bath of water, and water has a specific heat of 4,190 joules per kilogram per Kelvin. The bone and the water reach thermal equilibrium once the bone has absorbed 7,000 joules of energy from the water. So we want to find out which one of the following statements is true. Okay, so we're going to work through these one by one. So we'll look at option A. The temperature of the bone has increased by 2 degrees Celsius. So remember that you can actually calculate how much the temperature would have increased by. So in our first question, I showed you that equation. Q, the amount of energy, heat energy that's absorbed or transferred, is equal to the mass times the specific heat capacity multiplied by the change in temperature. So we can calculate the change in temperature if we just rearrange this equation. So that's going to be delta T is equal to Q over MC. And our Q, so the amount of energy that was transferred is 7,000. And the mass of bone is 0.1 kilograms. And the specific heat capacity is going to be 3,500. So that will give you a 20 degree Celsius change in temperature. Okay? And if the bone is absorbing energy, then it's going to increase in temperature. Okay, so statement A is false because it's going to increase by 20 degrees Celsius. So that means that option B must be true because that's we've just calculated that. So option C is our true answer. So you just got to be careful here because if you had used, oh no, not really. Well, actually, yeah. So then C is false as well, and then D, it says the initial temperature of the water was less than the final temperature of the bone. That's obviously false because the initial temperature of the water would have had to have been greater in order for it to transfer energy to the bone, right? So whatever energy that the bone is gaining is coming from the water. Okay, so whenever you get these problems, just treat it simply. So if one's gaining energy, the other object has to be losing energy. Okay, so then how much energy has the water lost? The water will have lost 7,000 joules of energy, right? But that doesn't mean that the water will have decreased. The change in temperature of the water doesn't have to be 20 degrees. Because that depends on the amount of water that you have and also depends on the heat capacity of the water as well, okay? So that's the amount of energy that's lost and gained will be equal, but that doesn't necessarily mean that the temperature change will be the same. So that's important to realize that. So the answer there is B. Number 6, the spherical stainless steel head of an artificial hip is stored at a temperature of 4 degrees Celsius and then it's warmed to 37 degrees Celsius before being implanted. The coefficient of linear expansion of stainless steel is 6.9 times 10 to the negative 6 per Kelvin. What's the fractional increase in the volume of the head of the hip implant? So what they want is delta V over VO. So this might look a bit tricky because you're like, what the hell are they asking for? But if you just go back to your change in volume, your thermal expansion equation, you'll remember that you have delta V is equal to VO times 3 times the thermal coefficient multiplied by the change in temperature. So what you need is delta V over VO. So what you can do is just divide both sides by VO. So if you divide both sides by VO, that's just going to turn this side into delta V over VO. And then the other side is going to be your equation, right? So that's going to be how you're going to find out. Okay, so note here that they have given you the linear coefficient of expansion, So that means that you have to multiply that coefficient by 3 in order to get the volumetric coefficient. So delta V over VO is equal to 3 times our coefficient times delta T. So that's going to be 3 times our coefficient, which is 6.9 times 10 to the negative 6, times our change in temperature, which is going to be 33 degrees. So that's going to be 6.8 times 10 to the negative 4. Okay? And that has no units because it's just a fraction. Okay? Right. And one thing I'll mention is that sometimes they will give you the volumetric coefficient. So if it said the coefficient of volumetric expansion is 6.9 times 10 to the negative 6, then you wouldn't have to do 3 times because that means that it's already been multiplied. That's for the volumetric expansion. But here they've given us the linear expansion coefficient, which is why you have to multiply it by 3. Okay, so make sure you read it carefully before you do these calculations. Yeah, and there have been examples where they give you the volumetric coefficient. So number 7, we have a sealed container at a total pressure of 300 kilopascals, and it contains a mixture of nitrogen and oxygen. There's 2 moles of oxygen and 1 mole of nitrogen inside the container. What's the partial pressure of oxygen in kilopascals? So the total pressure is going to be made up of several different gases. So in our container here we have 2 different gases, and each of them are going to exert a certain amount of pressure, and we call that the partial pressure of those gases. So if only that gas was in the container, how much gas would it be, or how much pressure would it be exerting? And so that means that the total pressure is the sum of the partial pressures of the gases that are within it, and so on. So you could have, if it's just one gas in there, then it'll just be the one partial pressure, and that will be equal to the total pressure. If you had 2 gases, it'd be P1 plus P2. If you had 3, it'd be P1 plus P2 plus P3, and so on. Okay, so the thing that's going to determine partial pressure is going to be the number of moles that are present. Okay, so we have a pressure of 300 kilopascals, and we know that there's 3 moles total inside the container. So that means that for each mole, must equal 100 kilopascals of pressure. Okay? Since there's 3 moles and there's 300 kilopascals, and so that means that because there's 2 moles of oxygen, the partial pressure of oxygen just will be 2 times 100 kilopascals, which is 200 kilopascals. Okay? So it's really quite a simple question. And going on from that, so the partial pressure of nitrogen would be 100 kilopascals. So then you've got 200 kilopascals of oxygen plus the 100 kilopascals of nitrogen, which combines to give our total pressure of 300 kilopascals. Okay, so you see that this equation at work. All right, so next one, number 8. So this is a nice one to like illustrate all the kind of things that people kind of get confused about with gases, with ideal gases. So we've got a container with a volume of 1 meter cubed, and it holds a mixture of argon gas and neon gas. So there's 2 moles of argon and 1 mole of neon. These two gases are monoatomic and are in thermal equilibrium. So given that the molar mass of argon is 40 grams per mole and the molar mass of neon is 20 grams per mole, which one of the following statements is false? So we're going to look through each of these statements one by one and look for the false statement. So A, the temperature of the argon is equal to the temperature of the neon. So this will be true because we've been told that the gases are in thermal equilibrium. So thermal equilibrium means that the temperatures are equal. Okay, so if you have two objects and they say they're in thermal equilibrium, it means they both have the same temperature. Okay? And then, so B, so A is true, so we'll move on to B. The partial pressure of argon is less than the partial pressure of neon in the container. So what did we just say? We said that the thing that determines partial pressure is going to be the number of moles of that gas. So which gas do we have more moles of? Argon, right? So we're going to have a greater partial pressure of argon. So B is going to be false because we have more moles of argon, which means the partial pressure should be greater, not less. Okay? And then C, the average kinetic energy of the argon atoms is equal to the average kinetic energy of the neon atoms. So temperature, what temperature really is a measure of the average kinetic energy of the atoms or molecules that make up that object. So if you have a block of metal, it's actually made up of billions and trillions of individual molecules that are held together. But if you went down all the way down to like the microscopic level, then those molecules, it might look like it's standing still, like it's stationary, but if you look at it at the atomic level, they're actually vibrating and moving. So because they're moving, they're going to have kinetic energy. So the temperature is a measure of the average kinetic energy of those molecules. And so that means that the higher that the temperature is, the hotter an object is, the more kinetic energy that those molecules will have. So the faster those molecules will be moving. So that explains why if you touch a hot object like a frying pan that's been on the stove, it looks like it's staying still, but the metal atoms in the frying pan are actually moving really fast. So when you touch it, it's actually transferring that kinetic energy into the molecules in your skin, which then break all the chemical bonds in your skin and causes you to get burnt, right? So that's what's happening there. It's so important to understand that, and that means that. So we said that the argon and the neon are in thermal equilibrium, which means they have the same temperature. If they have the same temperature, it means they have the same average kinetic energy. Okay, so C is going to be true. And then D, the average velocity of the argon atoms is less than the average velocity of the neon atoms. So this one's something that confuses a few people. Sorry. So we know that the kinetic energy is going to be the same, the average kinetic energy. So the equation for kinetic energy is equal to half mv squared, okay? And we've been told that the mass, the average mass of argon is greater than the mass of neon, right? So in order for argon and neon to have the same kinetic energy, argon would have to be going slower, right, in order to have the same amount of kinetic energy, right? Because if you have a larger mass and you're going at the same velocity, you're going to have a larger kinetic energy. So in order to have the same amount of kinetic energy, you're going to have a lower velocity, right? Yeah. Oh, it's because it says given that the molar mass of argon is 40 grams per mole. Oh, yeah. Yeah. So, yeah, for the same number of argon molecules, it's got double the mass. So that means that whereas the molar mass of neon is 20 grams per mole, so that's telling you how big each, well, not how big each one is, but you've got the same number, which is 1 mole, and which means that the mass of each individual argon molecule is twice the mass of a neon molecule. Okay? So that means that D is also going to be true in order to obey this kinetic energy must be equal rule. And then E, the total thermal energy of the argon is greater than the total thermal energy of the neon. So you might be a bit confused here and think, oh, well, we just said that the energies are equal, but that was the average kinetic energy, right? So that's the kinetic energy per molecule, but remember that there's twice as many moles of argon as there is neon. So there's 2 moles of argon and 1 mole of neon. So the total thermal energy in the argon is going to be greater, right? Because even though they have the same amount individually, if you add all of them up, there's going to be more argon than there's neon. So E is also going to be true. Okay. Cool. Any questions about that one? Number 9, we have a fixed quantity of an ideal gas, which is held in a cylinder with a movable piston, which is weighted down to produce a fixed pressure in the gas. The initial volume of the gas is 5.0 times 10 to the negative 3 meters cubed. The temperature of the gas is changed from 40 degrees to 80 degrees. What's the new volume in meters cubed? So this one here, you've got a change in the conditions, so the change in values. You've got an initial value and a final value. So in these, and if you're dealing with a gas, then the equation that you're going to use here is going to be P1 V1 over T1, where that's pressure, volume, temperature, is equal to P2 V2 over T2. Okay, so that's the equation that you're going to use if you have a change in conditions and it's related to a gas. Okay, so in our first sentence there, it says we have a fixed pressure in the gas, so the pressure doesn't change. What that means is that P1 will equal P2 because pressure isn't changing, and that means that we can, if they're the same on both sides, we can cancel them out. So we'll cancel P1 and P2 out. And so then we want to find out the new volume, so that's going to be V2. So we're after V2. So just multiply both sides by T2, that's going to just go up there. So that means V2 is equal to V1 times T2 over T1, okay? So initial volume was 5 times 10 to the negative 3. So that's going to be V1. Our T2, our final temperature is 80 degrees Celsius. So here we have to convert Celsius into Kelvin. So the way that we're going to do that is just to add. So AT was our value in Celsius. We're going to add 273.15 to that value. Okay, I like to keep the 0.15 on the end just to make it more accurate. I don't think it really matters. Like, you should be able to get away with not putting that on. So you could just do plus 273, but I just like to put it on because that's just how I am. So then that's going to be 353.15, and T1 is going to be 40 plus 273.15, which is going to be 313.15. Okay. And that will give you a final volume of 5.6 times 10 to the negative 3. Okay. Number 10, we have a rigid sealed container with a volume of 1 meter cubed, and it contains a monoatomic ideal gas. At a temperature of 20 degrees Celsius, the gas is at a pressure of 100 kilopascals. The container and gas are heated to a temperature of 55 degrees Celsius without any change in volume and with no leaks. So again, we're having a change in our conditions, right? So we're changing our temperature in this container. And we want to find out what the new pressure is in the gas after the temperature increase. So that's going to be the final pressure. So again, we're just going to use our last equation that we used. P1 V1 over T1 is equal to P2 V2 over T2. Okay, so this time we've been told that there's no change in volume. No change in volume means V1 is equal to V2. If it's the same on both sides, we can cross them out, cancel them out. So now we're just left with P1 over T1, P2 over T2. And we want, what we want is P2. So again, we're just going to move that up here. So P2 is equal to P1 T2 over T1. P1 is 100 kilopascals, so 100 times 10 to the 3 times our temperature, our final temperature. So T2, our final temperature was 55 degrees, so 55, we have to convert that into Kelvin, plus 273.15. That's going to be 328.15 Kelvin. Okay, so 328.15 Kelvin over our initial temperature, which is T1, and that's 20 degrees, plus 273, which is 293.15. And that will give you 112,000 kilopascals. 112,000 pascals, which is equal to 112,000 kilopascals. Okay, so our last one now. our last one, we have an increase in the total internal energy of the gas. So internal energy is just kind of like the total energy that it has, like the gas has, and that includes thermal energy, and usually that's going to be it. So you can kind of just think of it as all of the energy that the gas has, and the symbol that we use for that is U. So U is the internal energy. So again, it's a type of energy. All right, so the equation for U is equal to 3/2 times N times R times T. Okay, so the total internal energy in an amount of gas is going to be equal to 3/2 multiplied by the number of moles, which is N. So that's number of moles, and R is your constant. So R is equal to 8.3. For chemistry, for physics, you can just use 8.3. I know in chemistry you have to use like a couple more significant figures, but you can just use 8.3 for physics. And then T is your temperature in Kelvin. Okay, so what that means is that it only really depends on the temperature. So as your temperature of the gas increases, the internal energy of the gas will also increase, right? Yeah, and so we can now just add delta to it. So now we can say that the change in internal energy is equal to 3/2 times N times R times the change in temperature. Okay, so that's the same equation, but now we're just looking at the change in energy, which is correlated to the change in temperature. And one thing I need to point out here is that this 3/2, the 3/2 is for monatomic gases. So monatomic gases, you're going to use 3/2, whereas if it's a diatomic gas, you're going to use 5/2. So monatomic gases would be like helium, neon, and I haven't done chemistry in ages, so I don't even know what else there is. And then diatomic gases would be like oxygen, which is O2, nitrogen, which is N2, yeah. Okay, so it just means that for the same temperature, diatomic gases are going to have more internal energy because you don't really have to understand why, but it's just going to have like more like degrees of freedom, which is what this is representing. That number represents like the number of degrees of freedom that it has. Yeah, so the equation that we'll use for this problem is going to be this one here. And we're going to use 3/2 because we've been told that it's a monatomic ideal gas. So we need to find out the change in internal energy, and we know what R is, and we know the change in temperature, but we don't know the number of moles, so we need to calculate the number of moles that we have, right? So R equals 8.3. So we need to find out the number of moles. So we can use this equation now. So PV is equal to nRT. And we're going to rearrange this equation for N. So N is equal to PV over RT. Okay. So this question number 11 is continuing on from question 10. I should have told you guys, sorry. It's so this is continuing on from question 10. So we can use, so what we can do is we can use P1, V1, T1. So that's the pressure, volume, and temperature before the increase in temperature, or we can use P2, V2, and T2, which is the pressure, volume, and temperature after the increase in temperature. But what's important is that if you use P1, then you use V1 and T1. And if you use P2, you use V2 and T2. They're both going to give you the same answer. Okay, but it's important that if you're going to use the before values, you use the before values. If you're going to use the after values, you use all the after values. Okay, so for simplicity, we'll just use the before values. So that will be the pressure before the temperature increase, which was 100 kilopascals. So 100 times 10 to the 3 times our initial volume, which was 1 meter cubed, and then our R value, which is 8.3, and then our temperature, so our initial temperature, which was 20 degrees Celsius, so we have to convert that into kelvins. 20 plus 273.15 is 293.15, and that will give you 41.1 moles. So we figured out the number of moles that we have. So then delta U is equal to 3 over 2 times 41.1 times 8.3 times our change in temperature. So 55 minus 20 is going to be 35. That's our change in temperature. And that's going to give you 17,909 joules, which is 17.9 kilojoules. Okay? All right. So that's it. I'll be starting the advanced tutorial in 15 minutes. Cheers. Yeah, feel free to come up and ask me questions if you have anything you're curious about.